right. How you guys doing? Doing all right? So just as a reminder here, I'll be here for this week and then gone next week while you take your exam. So next week you'll have, my TA will pass out the exam, so be kind to her. She'll try to help you if possible. I've given her some instructions. She's going to take a look at the exam, see if she has any questions for me. But she's not taking this class, so don't expect her to know every last thing. And of course, you're not supposed to ask her the answers, so she shouldn't give you any answers anyway. I'm generally a little bit generous when I'm answering your questions to try to, maybe provide a little hint or suggestion if I can without giving it away. But you can just expect she's going to do her best, and I'll take it under advisement if I made some sort of mistake. Yeah. The exam's on Tuesday, and then on Thursday next week, you'll have a guest lecture from another grad student of mine on advanced oxidation processes, kind of following up on what we're covering today, sort of an advanced disinfection and treatment strategy. So that's the plan for next week. This week, today we're going to cover disinfection. I've got to go a little quick because I have a fair bit of material and I like this topic, so got a lot for you. And on Thursday, we'll have an exam review. So if we didn't spend enough today, or if you'd like to come back and revisit the problems on membranes that I kind of sped over last time, we will catch up one way or the other, answer any questions, and prep you for the exam. So that's the plan. The exam itself, I designed it to be 30% of it is kind of multiple choice. None of those have a calculation involved, or at least any significant calculation involved this time. So there are 9 questions, 3 on granular filtration, 3 on membrane filtration, 3 on disinfection within the multiple choice or true or false segment. Then there are 3 more questions, each one for each of those 3 topics. That require some calculations, and the kind of free response, that's 70% of the grade. So that's the way I've set it up this time, as you'll see next week. All right, so let's get started. So I always like to start off asking you, do you know the difference between sterile and disinfection, or disinfected? So how many of you think my water has been sterilized? Show of hands, anybody? I think it's properly disinfected now that I haven't washed it in a while and I've been drinking out of it. Now you're not sure. Like, how gross are you? Okay, so the deal is sterile means you've pretty much eliminated any possibility for any organism to reproduce. So if you sterilize something, what you're actually referring to is preventing it from reproducing. So you can actually say, let's say a donkey is a sterile animal because it's a crossbreed, or sorry, a mule, right? Crossbreed from a donkey and a horse, or there are sterile offspring in certain cases of genetic crossbreeding, right? So you can sterilize, you could say, my dog has been sterilized. It's been neutered. It cannot reproduce. It's alive, but it's sterile, right? There are cases where we can sterilize some bacteria, but they're still alive. They could even produce a toxin, but one little bacteria producing a toxin is not going to be enough to do anything. And it's going to die before long, and it will never have reproduced. Okay, so when we say sterile, it's very different than disinfected. Disinfected, again, you could have living pathogens that are able to reproduce, but if there aren't enough to cause an infection, maybe that's disinfected enough. We say disinfected, meaning it's no longer infectious, can no longer give you an infection. So as we think about what it takes to provide disinfection of our water, and we think about the fact that there are probably literally millions, if not billions, of living organisms in the water I'm drinking, we realize that what type of organism matters, right? Is it the same stuff that's in my mouth, in my saliva? Is it algae, harmless algae? Are there viruses that are infecting those algae cells? Probably all of the above, to be honest. There's a good chance there's all that type of stuff happening. But it doesn't bother me. None of that is providing an infectious dose. Now, if I added some Vibrio cholera into there, maybe there's a problem. Or maybe if there's not very many of them, maybe I'm fine, as we'll talk about in a little bit. So, disinfection then means we're going to treat our water to a point where things are not going to cause an infection. So that usually means we need to know something about how infectious is a pathogen and how many are typically in the environment so that we can treat accordingly. So, kind of big picture here, as we consider our drinking water treatment type of system, we will almost always disinfect after these other processes we've often in a plug flow reactor type of scenario to achieve the disinfection that we need. Okay. At that point, we send it through our distribution system, and we also will aim to design our distribution system to retain enough chlorine. Sometimes we even add chlorine uppers along the way to make sure that there is some residual by the time it is poured into my bottle so that it's helping keep at bay anything that could be growing in the pipes. All right? So there's usually, or there is some requirement that we have, I think 0.5 milligram per liter of free chlorine is our typical target. I think that can be up as high as 1.5 milligrams per liter. That'll keep some residual disinfecting capability, preventing, let's say if we install a new pipe. Well, that's kind of a dirty process in the ground. We probably could have added some pathogens into our water system. In addition to flushing it, we have residual chlorine to help deal with that type of situation, right? We're not going to sterilize the ground and everything in the pipes before putting them in. It's just not practical, not going to work. Plus, pipes will eventually leak. We pressurize them to be pushing water out, but that doesn't mean bacteria can slowly work their way in and have some exposure. So we just need to keep the bacteria and other organisms at bay, not letting them grow and propagate to become present at infectious levels. All right, so the type of pathogen matters, and matters for a few reasons. One, how likely is it going to make us sick if we're exposed to it? How many pathogens does it take? How vulnerable are they to disinfection? How do we design a system to adequately disinfect them? So, tiny bit of biology here, doesn't matter a whole lot, but you ought to know that viruses, they're small, they're basically just proteins, maybe with some lipids, and it's basically a very large molecule, or an accumulation of lots of molecules together to make some big blob. Too small to see in a this is an electron micrograph here, they would probably be about that big or smaller, right? If these are bacteria that we're looking at right here, and this is 1 micrometer, that's 1,000 nanometers. Well, a virus typically is about 50 nanometers. So there's a little virus, okay? Something like that. Whereas up here, there would be bacteria. And then if we put a protozoa, these are a third type of organism. These are actually closer to humans in that they have full cell walls. So there's the viruses, there's debate about whether or not they're living. They can reproduce, but it's something else that's living that's doing all that function. It's kind of like just a DNA insertion the virus does. The bacteria, they are bigger. They have some cell membrane, but they don't have a full cell wall. We call them prokaryotes. Then we have the stuff like Cryptosporidium or Giardia. So you probably by now have taken a look at that reading assignment, Cryptosporidium. It was the big deal for that. These are single-celled organisms, so not nearly as big as a human, but they tend to be like 5 to 10, maybe 15 or perhaps 20 micrometers. So if this is 1 micrometer, we need 20 of these. So on this little micrograph, these are larger organisms comparatively. Still single cell, still, individual things that can give us an infection. So they're still microorganisms, we would call them, but they're easier to filter. They're harder to kill with chlorine because their wall is a little more robust and they can make a little cyst and defend themselves against the environment. But there's usually not quite as many of them out there. So if they do cause an infection, whatever host organism will be producing some of them, but not nearly as many as, let's say, the viruses or bacteria. So we're kind of going from smallest to largest here, and in general, it's inverted in terms of the number that are produced with some infection. An infection, by the way, is going to be that process of an organism multiplying. And whatever it's doing as it's multiplying can be the problem, right? So we have lots of bacteria multiplying in our guts. It's helping us process all the food that we eat. But most of them are not harming us. They're in symbiosis with us. We're happily letting them digest food and sending them on their way and so on. We get food, they get food, we're all happy. But some of them might start producing a toxin. Or if some of these in our lower intestines get to the wrong spot, perhaps then they're causing an infection, causing problems in our upper intestines. Let's say that fecal-oral route of transmission. Something that was there is now where it shouldn't be and giving a problem, right? So we can see that depending on where they are multiplying can be a bad thing. They can be eating away at our tissue or something, right? There are different ways of the infection being important. So it turns out that things like noroviruses, rotaviruses, even poliovirus is certainly a foodborne, waterborne infection. So good safety, hygiene, and disinfection is a solution to prevent poliovirus, prevent all of these. These typically only takes 10 to maybe 20 viruses to give you an infection. So it doesn't take many. And when you do have an infection, you end up producing a lot. So a lot are then discharged, can be a pretty big problem. So if you've ever had food poisoning or heard someone had food poisoning, chances are pretty good it was actually a food infection, and it was probably one of these viruses. Probably not poliovirus, but probably like a norovirus, maybe a rotavirus. If it's something that you ate something sketchy for lunch, then you had some dinner, but you weren't feeling quite great, and in the evening you got sick, you thought it was dinner because you got sick right after. It was probably your lunch, and somehow the hygiene chain broke down, and you got sick from a virus like that. If it took 24 hours, which is kind of hard to tell because maybe you thought today was sketchy, but it was really yesterday's food, maybe it was something that takes a little longer to start reproducing rapidly, something like a bacteria. So if these typically hit you after 8 to 24 hours, these guys, bacteria, E. coli, salmonella type stuff, first of all, these take somewhere like Vibrio cholera, you kind of need something like 10 to the 6 to 10 to the 7 range organisms to get you sick. So to get cholera, you need to ingest a lot of cholera. And I'll explain in a minute why. E. coli and things, maybe these are a little less, 10 to the 4 to 10 to the 6 range, salmonella as well. And these also tend to be more like 24 to 48 hours before you get sick. Then you're sick for some time, depending. Now, some of these will produce a toxin and will poison you, and could poison you even just simply by producing the toxin. Then maybe you kill them all, but the toxin is still there when you eat the food, right? So you could have food poisoning. The poisoning part would happen immediately. You ingest poison, you get sick because you're poisoned. That's what we really call food poisoning. All of this applies to water, which is why we're talking about it, but food is also related here. So, oops. So if you have a food infection, you might have, let's say, salmonella. It's causing problems. Then it starts producing a toxin, and the problems are worse. So it could be both. You could be poisoned because of the infection, or it could just be an infection. You're sick, things aren't right, it's no good. Then there's the protozoa for, let's say, Cryptosporidium giardia kind of stuff. There's also amoebas. But these guys, really, it's somewhere between 1 and 5 range cells to get you sick. And then I think it can take up to days or maybe weeks before you really get the infection. And it tends to be an ordeal that lasts several months. These don't clear very easily. Conventional antibiotics are no help because these are not bacteria. They're something different. So they're a bit of trouble, but healthy people usually get through it okay. If you keep your nutrition, hydration up and everything, should be fine. So this concept of dose making the poison. If you had one cell creating a toxin and living where it shouldn't be, you probably would never know it because it's going to die. They probably live 24 hours or something. It'll die. It'll produce maybe not even a nanogram of that toxin in your whole body. No problem. But if you have lots of these cells and they're growing and multiplying and creating lots of toxin, there you go, you have a problem. Now the big question is, how do we know how many it takes? How would you study that? Try it. Yeah, so you could maybe test it on yourself, or maybe, I think this is what the CDC did. You recruit a bunch of college age students or people who are like, hey, you want $1,000? I'll put you in a hotel. I'll feed you all the food that you could ever want. All you have to do is just take this sugar pill. May or may not have something else in it. And by the way, this is kind of a hospital type hotel facility. So we're just going to keep you happy and safe for the next week. You might get sick. But you'll earn $1,000. How many of you would do that? Maybe, right? It's like, okay, because they also have to test some that are a placebo, right? You might just get the sugar. That's great. I get free food, free Wi-Fi, all this, get to hang out, whatever. You might be the lucky one, and you might be asymptomatic. So that's another thing that can happen, right? You might have the infection, be infected, but nothing happens because your body's like, whatever, don't care. That can happen sometimes as well. So funny thought of how you go about making these studies. Probably costs a fair bit, and probably paying the participants is the least of the trouble. But interesting thing there. Vibrio cholera, we're going to talk a lot about today. That one takes a whole lot because it's vulnerable to our stomach acid. Some of these other bacteria are also, but cholera in particular is quite vulnerable. So we have some natural protection, at least from some of these. And in the case of cholera and the like, it's a good thing because how many of you have ever had raw oysters? Anybody? Okay, a few of you. You might not ever again, we'll see. Oysters tend to be really good at grabbing stuff from the environment to munch on it, filter feeder kind of stuff. But it turns out that viruses and bacteria tend to stick, and they're not necessarily digested by the oyster itself. So they kind of get caught up into the oyster and just stay. So if you have some wastewater discharge upstream that wasn't completely disinfected or wasn't disinfected or something, well, there's a decent chance that some of these pathogens might be accumulating there. So if you're going to eat raw oysters, do it on an empty stomach. And maybe add a little lemon juice or something to add a little extra acid. At least you're vastly decreasing the chance of getting this, doing it that way. So if you have a full stomach, your acid's already kind of diluted and maybe neutralized by other stuff. So if you're going to eat the raw oysters, do it at the beginning of your meal. It's my tip, my suggestion. Might not save you. I had a chance to try raw oysters once, actually, in the Mediterranean, and so I did try it. I was fine. So took a gamble. It was fine. It was a cool experience. Okay, so keep that in mind. All right, so I want to talk about a guy named John Snow. Not not this one. He knows nothing. Not my brother, who's also Jonathan. He also might know nothing. No, kidding. But the guy that is termed the father of epidemiology. This is a Game of Thrones reference, by the way, in case you didn't get that. So there's a guy named Jon Snow. He was a doctor kind of in England, in London in the 1850s. And it turns out cholera, Vibrio cholera, was a big problem. And there's a really neat kind of, I don't know if it's historical, fictionalized history book, I guess, meaning they added conversation, they added, he went here, he did that, he talked to so-and-so. They added fictitious actions based on real life happenings. So it's actually quite a nice, easy read because it's well done that way. It's called the Ghost Map. And that's kind of depicting and describing really the first discovery of waterborne disease, in a sense. Talk a little more about it. It's not exactly waterborne disease. It was waterborne disease, and he thought he saw in a microscope that it was little things swimming around. Turns out his microscope probably wasn't powerful enough to see the Vibrio, maybe using algae or something and had it in mind. He was right that there was a particular pump, a well, in London that was contaminated and was the source of a very bad cholera outbreak. Now, this was kind of the first confirmation of the germ theory of disease, and we call him the father of epidemiology because essentially epidemiology is simply mapping disease or related things. I guess disease is probably general enough. So mapping diseases to see where it's occurring, to try to find why it's occurring, and to fix the issue. Okay, so that's epidemiology. We call him the father of epidemiology for this famous work in the 1850s. And this is the title of that book, or the cover page. And this is a copy of the map that he drew. Now, cholera is terrifying back in the 1850s because once you get it and you start having symptoms, you could be dead within 18 hours, maybe less. Literally, you could just be dead. And so what happened is, as this outbreak began, you would have families where in the morning you're fine, and by the time you're going to bed, half your family's dead. Like literally could happen. And you don't know why. You don't know how to fix it. You don't know what's going on. But that's happening all around the neighborhood. Absolutely terrifying. Okay? So if you can consider that's sort of the context here, take a look at this map. You see the dark squares. I've got another image, but and I'll come to that in a moment. But each of these bars, each little layer of the bar is one death. So you can see this neighborhood is essentially being ravaged by this plague, and this is why the plague, whatever kind of plague you're talking about, was a terrifying, terrible thing, as you might see from kind of historical literature. If you turn this on its side, add in the red here to make it stand out a little better, you can see some very large bars here where there's many fatalities in different homes in different areas. So with this going on, to map it was a big deal because then you could actually see each of these flags. That's a different well that people get water from. And so essentially what Jon Snow did was, and by the way, he never had any kids, so I'm not directly related. Maybe he had a brother or something. I don't know. I'd like to think so. I probably have some English in me, but at least not directly related. So he went out, once he had this map, kind of recognized that this little pump, the Broad Street pump well, and if you've ever visited London, and I think maybe some of our students did the study abroad, probably saw it, he basically removed the handle. Once he realized that was probably the problem, removed the handle, and the outbreak quickly came to a stop. So the deal is, oops, there it is. The deal is there was an infected infant in the house that was right by this pump. And it turns out that back then our hygiene was not so great, and your latrine system was not so great, and this was probably just a pit, honestly. Maybe there was some some sewage drain type of situation in the street to let your excrement head towards the nearest river. Gross. But that was about the best you could do. So in this case, whatever latrine pit was built into this house, it was actually right up next to the well. And this infant, turns out it's important that this was an infant because the infant probably survived. I think it survived, but it was not going to be sick as severely as an adult would be. I'll explain that in a second. And so it kept a perpetual infection, producing more cholera, feeding it right into this well, essentially the contamination, because the well was like a shallow well, you don't have pumps to go deep. So shallow well, excrement going into it, people taking water from that well and getting sick. So as soon as they removed the handle from that well, stopped most, if not all, of the source of contaminated water. Now, I meant to mention the reason cholera is so crazy terrifying is if you understand what our intestines are doing for us, normally they are taking water out of whatever we have eaten and drank, and sending it into our bloodstream. Right, so they are kind of water harvesting agents, so to speak, and helping us with that balance, drying out our excrement and keeping ourselves hydrated. Well, cholera, the way the infection occurs is it actually adds in a little enzyme or chemical or something and tells our intestines to reverse that. So then it's suddenly taking liquid from our bloodstream and discharging it out your stomach or out your intestines. And of course, you're excreting that. So you get extreme watery diarrhea, and the reason you might die so quickly is because of simple dehydration. Your body just cannot hold water anymore because it's all discharged. That actually means that today, almost nobody dies from it because we know how to keep people hydrated, even in severe cases like this. An IV with a saline solution would do the trick. Hydration salts and good water would do the trick, typically. So it's almost not a problem today. It would probably be very uncomfortable, but it was a big problem back then, and you didn't know what to do about it. Even if you did know what to do about it, are you going to drink more water? Propel the infection? You know, you're at least probably not getting better very quickly that way. So that was the story, and that's why it was so terrifying back then. And it's kind of a crazy case, a very stark case of why disinfection matters, right? A very clear illustration of that fecal-oral route of transmission that we are concerned ourselves with for a good reason. So that's John Snow, that's the ghost map. Wanted to give you that as a kind of case example of how we now see and appreciate the importance of disinfection, right? Okay, any questions? How many of you have been to London and seen that? Anybody? Okay, a few people. Cool. I still need to do that. That's a bucket list. Maybe I'll see if I have any relatives. All right. So now I want to talk about the disinfection strategies. One would be free chlorine. We talked a lot about that. This is, we can apply it as chlorine gas. It's a little dangerous to do that, but it's possible, and people do that. When you add chlorine gas to water, you could take Cl2 gas plus a water, do this. You will end up getting a Cl minus come out, and you will end up also with an extra H plus and then an HOCl. And the HOCl is really the part that is what we consider to be bleach, the free active chlorine. Now, we also have to remember that in itself, this free chlorine HOCl, or hypochlorous acid, is in equilibrium with H plus and OCl minus. So we could also add this in a different form. We could say sodium hypochlorite. You'll see this very likely on your container of bleach at home if you have one, where this would dissociate to give you a sodium and a hypochlorite. Of course, if you have hypochlorite or if you have HOCl, so OCl minus or HOCl, they're going to be in equilibrium with each other. So if you have one, you have some of the other. It depends on the pH. Okay. Likewise, you could also add the calcium hypochlorite. That would work as well. It turns out that HOCl is the stronger one. Okay, so HOCl is the stronger disinfectant. And that's very important to know because that means one of these is going to work better under acidic conditions where there are more protons. You're more likely to get this H added to the OCl. And if your bleach is under basic conditions, it's weaker. And it turns out for safety reasons and for the fact that you don't really want to absolutely oxidize and destroy anything you work with when you're cleaning, usually we sell bleach as the basic version. It's still plenty powerful, and you can have a lot of it. What you don't want to do is mix it with an acid to make it even stronger. You also don't want to make it acid because then you could have chlorine gas come off. In the right circumstances, it could be enough to kill you or harm you, right? Probably just harm you, but if you try hard enough, they could be dangerous. So typically for household bleach, we keep it basic. For disinfection, for the real strong stuff, effective, efficient, cost beneficial. For water treatment, we keep it slightly acidic so that we have plenty of the strong stuff. Okay, so that's the deal. The cutoff, the balance here is at pH 7.5. So as soon as we are at neutral or slightly acidic, then we have more of the strong stuff than the weak stuff. All right, there's another type of chlorine, a couple other types of chlorine we can talk about. One would be what is often called combined chlorine. That's when chlorine reacts with ammonia or other amines to give us chloramine, which is essentially, it looks like an ammonia, NH2, swapping out with a chloride for the last, instead of the last H plus, or H there. That would be monochloramine. We could also do dichloramine, or technically even trichloramine. Like that. Don't worry too much about those. Those are just the combined chlorines. We generally don't try to have too much of those. For our water treatment, sometimes we'll intentionally have a bit of the chloramine here, monochloramine, because it doesn't react very quickly and it'll stay in the water a little longer. So if we're sending stuff through the pipes, maybe we want a little bit of that to help keep our residual chlorine up a bit. If you've ever gone swimming and it feels like there's way too much chlorine, I hate to inform you, because this is kind of gross, but it's probably less chlorine than normal because more of it has been converted to chloramine, which means either somebody's been sweating a lot in the pool or probably somebody's been peeing in the pool. Because there's a lot of ammonia discharged. Sweat and urine are pretty similar composition. So if there's a lot of ammonia in the pool, then you get a lot of chloramine, and that's the stuff that stings your eyes and smells real strongly. The free chlorine itself is actually not too stingy, not too smelly. It'll be there, and it does a better job keeping the pool clean. So, hate to say it, but that's the situation. But maybe that's good because now you can say, all right, maybe just too gross. Now, it turns out that that doesn't necessarily mean there's like pathogens or something that makes you sick. It just sounds gross, right? I don't know. You do with that what you will. Then there's also chlorine dioxide, ClO2. Similar in principle, it's going to oxidize stuff, bleach stuff, as we say, kill microbes. It's a bit different, but kind of overall similar. It's potentially dangerous. You can add it as a gas. It doesn't go through the same equilibrium, so it's not affected by pH the same way. Not as commonly used, but it's overall kind of similar. Then we have ozone. We can use ozone, but it tends to leave the water pretty quickly, and it doesn't, even if it did stay in the water, it's going to react a little quicker as well. So this one, It's a natural oxidant. We have it in our atmosphere and everything, kind of photochemically produced from oxygen up in the upper atmosphere. We don't like it in our local atmosphere down low because it is a lung irritant, kind of irritates us. So we try to avoid pollution that would generate more ozone in kind of the troposphere down here. But in the stratosphere, we're happy that it does all that because it absorbs UV light. And it takes away a lot of the UV light that would otherwise hit us. So we can use that, but it's not going to stay a long time. It's not going to do what chlorine does for us in terms of stay in the distribution system. So it's a pretty strong option. It can help deodorize stuff. That's all great. And as we'll see, we can use it for advanced oxidation as well. Then we have UV light. Again, same sort of problem. It's not going to stay in the water, but we can expose water to UV and do disinfection that way. If we stop a moment and think about it, if the different pathogens are vulnerable to some of these, they might be less vulnerable to others. So for example, the big Cryptosporidium giardia, they're a little bit more resistant to some chemicals because they have this robust wall, but there's actually a lot more DNA in them, which is easier to hit with the UV light. So they're sensitive to UV and not so sensitive to the chemicals. The viruses are kind of backwards. Viruses tend to be so small that on average, you're not, for the same amount of dose, you're not necessarily going to strike each one with a UV photon when they're very vulnerable to the chemical. So sometimes it makes sense to use multiple. A lot of times the most practical thing will be to do some sort of treatment to do most of the disinfection and then add a little chlorine to hang out in the water until we are ready to drink it. A couple other things that we could do here. This is not necessarily disinfection. Sometimes to treat things like pharmaceuticals or tastes and odors or other chemicals we don't want in our water, we could do advanced oxidation. So we could take something like ultraviolet light and hydrogen peroxide or ozone or some of what you'll hear next week with my student. We can actually do it with chlorine as well under special circumstances. And we can do more than disinfection. So that's kind of an option we get with a lot of oxidants that can help us maybe clean up wastewater sufficient so that we can reuse it for some purposes. Maybe we want to make sure we've destroyed all the caffeine, all the heroin, all the whatever that's in our wastewater, right? It's true, right? One of the best ways to find, to test whether or not there is human activity in some remote area, if there's anybody nearby, check for caffeine in the water. If there's caffeine in the natural waters, there's human activity somewhere nearby. It's like a very robust way to check. And it turns out that, a lot of the pharmaceuticals that we might illicit, right, or legal, right, are discharged through our bodies and into our waste. So if we want to reuse wastewater, we got to take care of all that. So advanced oxidation is one of those options. Pretty good for that. Okay, so let me pause kind of and talk a little more about free chlorine, make sure we're on board with the chemistry, make sure we're remembering that HOCl is the stronger one, and explain why we want that slightly acidic conditions. Now we've talked about equilibrium chemistry a bit, and I just want to make sure you understand or clear on how this plays out in practice. So we're going to draw up our equilibrium equation like this. HOCl is in equilibrium with H plus and OCl minus. So when we talk about total chlorine, and this is total free chlorine, I guess, what we're really talking about is the combination of both forms of chlorine. And typically, we're going to do this in a moles per liter type of scenario. So the total moles of chlorine in solution would be the combination of those two. Now the proton, don't worry too much about it because it's not like it can be there or it can not be there. It's the chlorine that's taking the action. It's the chlorine that matters. And this H plus is either coming or going. It's a little hitchhiker. Yeah.
Sorry, you say HOCl is stronger than OCl minus. That's just in terms of disinfection?
It's a stronger oxidant in general. but especially for disinfection, right? So we'll say oxidizer, but really its ability to cause disinfection. And by the way, that's about 10 times stronger, is how we treat it. So if you accidentally have your pH incorrect, you could have 10 times less disinfection than you were planning, which could be a big problem. Okay, so we have this equilibrium set up, and we will describe that equilibrium with an equilibrium constant so we can know how much will be in one form or the other under a particular scenario. This is going to be we called it Ka for chlorine. It turns out this value is typically, at room temperature, something like 10 to the negative 7.54. That would mean the pKa, if we take the p doing like the negative log of something, would be 7.54. So you might have seen that before if you have some chemistry, but I'll give it to you if you need it, probably in this form. What we can say, based on that equation that we have for an equilibrium reaction, is that it's the products multiplied together over the reactants. And the way we wrote it up, well, the products are H plus, they're on the right, and, excuse me, not plus here. We have to have a multiplication here. My mind was up here. We have to multiply these, so H plus times OCl minus, divided by HOCl. So I know there's at least one of these problems on your homework, so we'll cover that a little more practice on Thursday as well. But this is how you get going with it, right? This is the starting point. Sometimes you might try to get these two as a ratio of one another. Sometimes you might ask yourself, well, what fraction of the chlorine is in one form or the other? I think our first homework probably had a problem on that. And so we can navigate from there. Okay, so sometimes you might need to set up a system of equations where you say total equals that, and you're given some information about the total. And then you have this other equation. So you could have a system of two equations and rearrange one of them so that you have one equation with one unknown. Okay, that's kind of the deal. It's algebra from here, but it's worth recognizing that you have to be familiar with what kind of algebra and the fact that you need to be dealing with this in moles per liter type of units. And understand what the problem is saying if it says we added 10 grams per liter of NaOCl, right? Convert that to moles of OCl to get that going. All right, any questions on this? Okay, so as an example problem, we'll take a quick look at this. If you have 15 milligrams per liter of HOCl, it's added to potable water for disinfection, and the final measured pH is 7.0, we could ask ourselves what percent of HOCl is not dissociated. Assume the temperature is 25 Celsius, and that would mean that our pKa or our Ka is around 10 to the minus 7.54, we'll say. So take just a moment to think about how you're going to solve this and what the problem means. I'm going to give you 2 minutes. Then I'm going to give you the big picture, the first part of the solution, and we'll probably move on so I can make sure to cover everything. All right, how's it feel? Looks like a lot of you making some progress. Anybody feel stuck or not sure? All right, so let me run this through with you here. So the question's asking what percent of HOCl is not dissociated. So first of all, we need to recall that the way people talk about chemistry and dissociation is when a molecule separates into parts, that each chunk here is kind of a unit. So the OCl unit kind of sticks together until it reacts and bleaches something. So the H plus is the part that can be added on or can dissociate away. And so what percent dissociated, is not dissociated, excuse me, would be what percent is in the form of HOCl. That's a fancy way of saying it, right? So percent of HOCl is the question, and how we need to answer that would be to take, well, we need things in moles per liter to do the equilibrium. So we need to find HOCl divided by the total, which would simply be HOCl plus OCl minus, right? That's coming from our total chlorine equation. Multiply that by 100% to get our answer. That means we need to find some way of connecting HOCl to OCl minus using the equilibrium equation, which will be H plus times OCl minus divided by HOCl. The other piece of information we have is that the pH is 7, which means H plus is 10 to the minus 7. Now, you'll also see we have one other piece of information, but you actually don't have to use it. That is the amount of HOCl added. So if you stop and think about it, it doesn't matter how much of the stuff you add. It's going to be dissociating to the same amount given that the pH is set, no matter what happens. So it doesn't actually matter how much we added up here, the 15 milligrams per liter. You could solve it that way. You could put in the numbers. You could convert from milligrams to moles per liter and go on accordingly. But at the end of the day, you're giving a fraction as a percentage anyway. So at that rate, we don't even need to worry about it. So from here, if you recall what we did previously, is one thing you can do is work on, from this side of it and simplify it a little bit so that you can get it as a function of something over here and do a substitution. So it turns out we could actually rearrange our Ka equation to say Ka, if we just divide both sides by the H plus, then Ka over H plus equals OCl minus over HOCl, which is really cool because we now have a ratio of these two that maybe we can find a way to set up that ratio over here. And then add this into our equation to solve it because we know these two pieces, right? So that's our kind of our goal here, is to set up something that will give us that approach. So if we take this guy on the right, divide the top and the bottom by HOCl, this could become, we can get our answer algebraically by saying 1 over 1 plus OCl minus divided by HOCl. Turns out that substitutes very nicely right there. So now we have one equation to find our answer. Given just those two pieces of information, right? The Ka and the H plus. So it's a little fancy algebra, but at the end of the day, it's two equations, two unknowns, do a substitution, find a way make it work. Okay, and this happens to be a pretty straightforward, well, maybe not intuitive, but straightforward way to do it. Okay, I'm sure you can algebraically find a different way there. As long as your algebra is fine, you could still get an answer. All right, make sense? Okay, I'm going to move on from here so we can cover a little bit more. One of the concerns if we're doing disinfection is the other stuff that's in the water that we don't really care about, but we might care about what happens when we chlorinate it. So we often have generic organic matter, meaning organic molecules that are just hanging around. These might come from soil, these might come from leaves, these might come from dead microbes, these might come from all sorts of places, and there's not a whole lot of it. The water can usually be fairly clear anyway, but they're still there. So if you imagine taking your tea, you have added, by making your water brown with a lot of organic matter, that's organic matter from those tea leaves. Okay, and we do that on purpose. We're adding a lot of it. We're letting it all seep out. We're heating it up so that it comes out easier. Well, in nature, and even in our wastewater systems, turns out that there's just a lot of organic matter that is kind of hanging around. In some cases, more so than others. You've probably seen the difference if you've looked at some bodies of water that are stained brown. You can maybe see through them, but they're still brownish. Versus others where you can see through them and they're just clear, not adding much color. So there's probably a difference in how much organic matter, and at least the nature of the organic matter, the color of them, right? So if we have a lot of organic matter in water, then we add in our chlorine. Turns out we end up creating a scenario where we are halogenating. We're adding chlorine itself, of course, but turns out chlorine also will react with bromide if it's in the water, or iodide, and even fluoride to some extent, and add these halides, these particular chemicals, atoms, to the organic matter, and sometimes that can be a problem. Sometimes we'll get things like trihalomethanes or haloacetic acids, which are kind of toxic and maybe even carcinogenic. So sometimes we will end up producing some bad stuff by chlorinating. If we have too much organic matter, and by the way, there are so many different molecules out there. There's just thousands, tens of thousands of different molecules that we could find, and maybe they've broken apart a little bit. Maybe there's no way we can identify, oh, this is the toluene molecule or whatever. They're just too big, too complicated, half a virus, piece of DNA, organic stuff from a leaf, who knows what it is exactly, but they all have these organic matter pieces, and most organic matter, organic molecules, have, at the end of the day, some typical functional groups. Maybe some have an aromatic ring, maybe some have a methyl group, or whatever type of group, right? You could look into organic chemistry. The point is, some of that will turn into toxic byproducts. So we call these disinfection byproducts. So when we chlorinate, we have to be sure we are not over-chlorinating, given that. That kind of puts a limit on how high we go with our chlorine concentration. If we go overboard, we can make some bad stuff. So we have to sometimes use a little less, allow ourselves a little more time, so that we have some typical ranges of how we operate. It turns out that if we don't design our system well, we might have some issues. And I think when I'm back after the second exam, I think I'll probably give you a seminar-style lecture on the Flint water crisis. Turns out one of the issues, among many, turned out to be they were creating a bunch of these because they didn't have a proper design in place to treat water from the Flint River. Okay, this also relates to the real core of how we do our math for disinfection. So all that context, because it's cool stuff, I think, to get to how we connect it to a mass balance. So we need some chlorine. It can affect pathogens in different manners. And that's what we need to account for in our mass balance. So there's a concept called contact time. It is exactly as it sounds. The dose of a disinfectant multiplied by the time with which that dose is in contact with it I mean, well, that's probably not the right way to say it. The concentration of our disinfectant times the time that it's in contact with our microbe would be in total the dose. That's the better way to say it. So when we do some chlorine dosing, or maybe even a UV dosing, in the UV case, it's how much light was exposed given some amount of time. In the chlorine or ozone or things like that, it would be the concentration of our chemical times the time that it was in contact. So we could have, and it turns out that our disinfection impact, our rate at which the disinfection occurs, is proportional to both. Meaning when we take our rate, I'll say the rate at which our pathogen is being inactivated, R of N, we can define that as negative, we're destroying or killing or inactivating the pathogen. Negative K, we have a rate constant, surprise, surprise, times C to the N power. This is going to be a little different because we're doing R on N. So far in the class, we have sometimes used C, sometimes we've used N. Usually we use N if it's something like a microbe or a particle, like a discrete number. Usually we use C if it's a chemical. So I'm going to continue with the book's way of doing this, and we're going to say there's a C to the N power here. This is our chemical. We'll talk more about that in a moment. N to the 1 power is our microbe, and it's a first order with respect to the microbe. So it's the rate at which N is changing, does depend on N to the 1 power. This means we have a first order, and it's the microbes, right? So N, well, I have it written right there, right? N is the number concentration of pathogens, number per liter, and C is our concentration of our disinfectant. That might be milligrams per liter, maybe it's millimoles per liter or something like that. Whatever our units are, we keep our units consistent and we're good. Now, this little n is not referring to the order. It's referring to a dilution factor. And usually it's just going to be 1. For an ideal reactor, for all of our work, we'll just treat it as 1. Okay? So this is a dilution factor. If you had a very poorly stirred reactor or poorly designed reactor or something, maybe we'd have to do something different. If your chlorine is only making it around in half of your reactor chamber, maybe that's 0.5, right? Don't worry about it. We're just going to leave it as 1. So that means that our overall rate depends on the chlorine concentration or disinfectant concentration, the microbe concentration, and when we integrate and do a mass balance, it depends on time. Okay? So pretty straightforward. This will be called Chick-Watson kinetics. The reason we call it that, there were a couple of famous scientists back around 1900, Harriet Chick and somebody Watson. They were the first to describe this and discuss this, and essentially this tells us that we have a first order reaction with respect to the pathogens, the pathogen concentration. Now, it also assumes that our chlorine or other disinfectant is approximately constant throughout. What you'll notice is if you had a changing chlorine concentration and our rate depends on how much is there, it gets complicated as your chlorine drops. We don't want to be that complicated, don't want to torture you with difficult calculus. It's not the point, right? So we're going to keep that constant, and it turns out that's actually typical in practice, right? So we assume C is constant, because otherwise I guess it could be a second order with respect to both the N and the C. But when we do Chick-Watson kinetics, this is the deal. It's pseudo first order. We can call it pseudo because it's technically would be second order because the chlorine could change, but in practice or pseudo fake, we're going to fake it and say it's first order. All right, that's just how we talk about it. So this is a pseudo first order reaction with respect to the number of pathogens that are there, and it works almost exactly like anything else we've done. Okay, there's just another constant in front of the K, which means we could actually combine that constant, the C, with the K and have an overall rate constant and compare that to, or distinguish that from, the specific constant, the K with no star, which we would call the coefficient of specific lethality. So the important thing here is that each coefficient is going to be specific to our pathogen and to our chemical. So K for ozone-destroying rotavirus is different than the K for chlorine-destroying cryptosporidium, right? Very slow for chlorine to get cryptosporidium, probably very fast for ozone to kill rotavirus, just based on how vulnerable the viruses are, how protected the cryptosporidium is. I think crypto is actually pretty vulnerable to ozone as well. So compared to chlorine, that could be different too. So this K, as written here, is not per time because it's accounting for the concentration of the disinfectant, because it would be times milligram per liter of chlorine or whatever. For example, chlorine. So the rate constant here has to account for that to make our units consistent. Or we can say, let's treat this like any other first order thing we've done and call it K star. And then we just know that K star is equal to K times C to the 1 power. And then our units will be like per minutes or per seconds. Okay, so everything becomes normal, just like we've been doing, if we just treat it that way. The one thing you need to remember is this K star then. This is what the Chick-Watson kinetics is telling us, is that, well, it's accounting for the K times the C. Okay, does that make sense? So if you had a K star and you had a concentration of your disinfectant, you could find the coefficient of specific lethality here. That would be no problem. Divide both sides by C. You got it. So it's very straightforward. Just you have to understand what the pieces mean. Okay? This also means once we do this integration, let's say for a batch scenario, then we end up with the natural log of n over n naught would be equal to negative kt. And here's where our contact time, this would be k star t, excuse me, which would also be equal to negative kc to the 1 power times time. And here's where our contact time shows up. So the rate at which we're disinfecting depends on C times T. Okay, so that's a very convenient thing. If we're short on time, we need to make our disinfection occur in half the time, we could double our concentration of chlorine. Unless we create all these disinfection byproducts, right? So there's caveats, but. Okay, does that make sense? Any questions? All right. One little particular example I have from research. I could tell you more about it some other time. This was a light-activated mechanism. We were taking oxygen in the water, just regular stuff we breathe, converting it with light, maybe some sunshine here, with some cool material to make this stuff, and then that was a disinfectant. Pretty neat little study. Like I said, I could tell you more about that. That was some virus. So this is real data I collected as a grad student. We could say, okay, the virus, it's a surrogate virus, not real pathogen, but acting like it. We could study that. So I wanted to bring up a few other slides, I guess, and a quick little example here as well. Before we go, just to give you an idea of what the UV side of stuff looks like. It's almost exactly the same, but I just wanted to give you a little flavor. Before we get there, I think, did we look at this problem already? No? Okay. So this is a problem where we can find a rate constant, find that coefficient of specific lethality, given some data. So this is a problem that honestly would be good to do in Excel. I'm going to read the problem and kind of give you a quick look at how to do it. So this wouldn't exactly be the right question for an exam because you kind of need to graph it and get the line of best fit. But I wanted to walk you through it real quick, I guess run you through it. We have data for HOCl, that's our free chlorine, the strong kind, disinfection of poliovirus at a concentration of 1.8 milligrams per liter. That data is shown below, adapted from some study in 1979. The temperature was 20 Celsius, pH was 6. Determine the rate constant of inactivation, assuming Chick-Watson model applies with an n value of 1. So now that kind of makes some sense to you, right? So we need the rate constant. So we need to find K. Well, we know dN dt should look like negative K c to the 1 power times n, right? Also n to the 1 power. So that's our starting point. Like we showed just a minute ago, we could say that we could derive this and say the natural log of n over n naught will get us to negative k c t. So if we take this data, that's essentially, we could plot it as concentration versus time. It'll look something like this. And we could get some curve fit there. But if we take it and convert the data a little bit so that it's in this form on the y-axis, it should become linear. And then we can get a line of best fit. And the slope of that line should be k star. Okay? And then we know k star would be equal to k times c. So with Excel, we could do that data transformation, then take that line of best fit, take that as our k star, and then solve for k. Now, if we want to be real fancy, we could take the fact that it gives us a temperature and a pH, find the Ka at that temperature and stuff. You're not tasked with temperature-dependent Ka, but that's a thing that you could do. And then you could say, all right, well, how much of it is in HOCl versus OCl minus? And let's calculate specifically for HOCl. It's already kind of acidic, so it's probably like 99% is HOCl. So for the sake of this problem, I might just say, let's just call it 1.8 milligrams per liter and solve it that way. Right, so maybe I make a shortcut. It's going to be off by 1 or 2% from reality. Maybe more, maybe less, but not too far from that. So we could just treat that as 1.8 milligrams per liter, or we could be fancy, do it right, get a more accurate number, and perhaps even report it in moles per liter. We'll say or convert and use equilibria. Okay, so that's it for this set of slides. I'm going to just breeze through a couple of slides on UV. And you're going to hear a little more about this as well from my graduate student. Okay, so that's the problem we just looked at. So UV light we could describe as a part of the electromagnetic spectrum. We see stuff in the range between waves that have 400 nanometers between their peaks, or troughs, however you want to define it. So here's our wavelength. We often use lambda to describe our wavelength. We can see stuff between 400 and 700 nanometers, or 800-ish. That's actually kind of a small window in the scheme of things. We have UV and eventually X-rays if we go far enough, and gamma rays and such like that. If you go higher, we get infrared and eventually microwaves and radio waves and stuff like that. So you're familiar with a lot of these things. The UV stuff, turns out sunlight does something like this. I probably have a graph for that. And so solar is something like this. And in the UV range, we get almost no UVC, which is good because that's the stuff that damages DNA real bad. So UVA and B can cause some of those reactions like I was showing you in the last set of slides where you make this little single oxygen thing and it can harm stuff. So we get oxidation events, and you can get a sunburn from UVA and especially UVB. It's just intense light. It activates some chemicals, but it's not causing what we call cross-linking of your DNA. That's the bad stuff. Thankfully, ozone absorbs all that, so does oxygen before it gets here through the atmosphere, because the sun's shining a lot of it. Thankfully, we have an atmosphere taking it away. But that's the stuff we use to kill microbes. So if you ever work with a UV lamp that's germicidal, don't ever let yourself expose yourself to it, especially not your eyes, because that's going to cause serious harm, potentially blindness. Easy to protect yourself from it because almost everything's absorbing it. That's a good thing. So your glasses probably are protective, but make sure you're well covered if you're going to ever be exposed to it. So anyway, that's the stuff that we use. That's the stuff that does the action. And we'd probably put it in a chamber where we're exposing water as it's passing across a lamp. There are some challenges there because how do we keep the lamp itself clean while it's submersed in the water? It's going to get gunked up, and then how do we clean it? We can't use any normal or typical just material. UV's not going through this thing. UV's not going through your Coke bottle. UV's not going through your standard glass. You have to have very fancy quartz, or a very specialized polymer will let some of it through. And then even better if you can use some slightly different wavelength. So it has to be very special. This turns out to be a big expense, is cleaning quartz that's very fragile, easy to break. It gets gunked up with stuff. So in practice, UV treatment can be a good option, but there's a few challenges. Cleaning being a big one. It's an example of, you might see labs with a UV chamber keeping the workspace clean of microbes if we're a biological lab. This picture, there should be a glass sash here. You can probably see some reflections on it. That's actually protective. That glass itself is going to absorb all that UV. You can still, it's the blue light's passing through, so you can still see that, but the UV is stopped. If we take a close look at the UV range, the light that we just saw should be a low pressure mercury lamp, has a little bit of mercury vapor in it. It's excited by the electricity we put into it, and it's emitting light right here. That's about 254 nanometers. Turns out DNA absorbs light or photons about in this range. That's our germicidal effectiveness range. So as we approach where sunlight happens, we have just a little overlap where it's pretty bad, okay? But it's tiny. So that's good. That also means sunlight doesn't do a great job disinfecting. It takes a long time. Some of this light can do it. It's just very slow. So we want something that has a big emission over here. That's the interesting stuff. Another example of where that germicidal curve comes from. Here's DNA absorption by cryptosporidium and MS2. More of the same. What happens when we expose DNA to this type of UV light is at certain points, if you think of our DNA strands as a zipper, at certain points you put superglue in between prongs of the zipper. So it can no longer unzip or rezip. There are sometimes some cellular mechanisms that can try to repair it, but usually what happens is once you dimerize right there by that photon happening, now when the typical enzyme comes along to unzip and code things and read the information and make more proteins or whatever, it gets stuck. Zipper gets stuck, can't move, and you can no longer use it. It's a big problem. So that's why it's effective. That's why we don't want that for ourselves. And that's the thymine-thymine dimers that form. It's not every single part of the DNA, but it happens often enough that those are next to each other. And there's, I think, a couple other places that are vulnerable in the same way. So the point of almost all of this is when we do our disinfection, we need to expose all of our water to, or all of the bacteria in the water or pathogens to our UV. Can't have particles. We have to account for how the light gets dimmer and dimmer the further it goes through. It's especially true for our UV. And stuff like the organic matter can also affect it. So we can't have too much organic matter, otherwise it doesn't work very well. Quantification-wise, all I'm going to say is it's the same thing as that Chick-Watson stuff. All we have to do is convert, instead of a chlorine concentration, to a UV dose. Okay? At the end of the day, and I didn't put UV on your exam, but I could have, because it's just the mass balance. I knew I was going to run out of time, so I was careful not to quite do that. But I could, because it's just a different K star here. Whereas the intensity of the lamp is kind of like the concentration. And this uppercase lambda thing is just the K. So it's the same deal. The math works out the same. You're dosing, it's a dose times time, or the intensity in this case instead of concentration times time. It can all work out so that it's how does the mass balance work given some exposure and some number of microbes exposed. Another way to say it right there. And here's an example problem if you cared to look. Like I said, I didn't put any UV directly, but I certainly could have. All right, we did it. We'll see you on Thursday.